So if you've got a large positively charged plate, we should expect electric field pointing outwards in both directions away from it. So on the left side, towards the left. On the right side, electric field towards the right. And among other things, that tells us information about what would happen to a test charge. Let's say we had a small charged object right here. Let's say positively charged. Small positively charged test object here. That's going to experience a force in which direction?
The same direction of the electric field.
Right. Yeah, which in this case would be to the right. So that's because the force on the test object is going to be the charge of the test object times the electric field at that location. Electric field at this location is to the right. Charge of the test object is positive. So the force is going to be in the same direction as the electric field, but with magnitude equal to charge times electric field. And in general, I tend to think of the electric field as a description of that location's ability to apply a force to a test object, even if there isn't a test object there. On the other hand, what if we put a negative charged object here? If we change this to a negative charge, what difference would that make?
The force would be pointing. Oh.
Mm-hmm. Yeah, should be the exact opposite direction. Again, because force is charge times electric field. And if we multiply a vector by a negative scalar, that reverses the direction. So the force vector here will be in the exact opposite direction of the electric field vector. And this matches what we should expect more conceptually, that a negative test charge gets attracted towards the positive source plate. But that can be explained completely using the idea of electric fields as well. Any questions on that so far? Also, if we were to draw out some equipotential lines, how would we draw out the equipotentials in terms of where the voltage is going to be a certain value? Yeah, because the equipotential lines should be perpendicular to the field lines. Since if you travel with the electric field, what's happening to voltage?
Decreasing.
Yeah, if you travel with the electric field, you go to lower and lower and lower voltage. Travel backwards against the electric field, and you go to higher and higher, higher voltage. So to not change the voltage, you have to travel in which direction relative to the electric field?
Perpendicular.
Yeah, if you travel perpendicular to the electric field, you're not changing your voltage at all. So any vertical line, in this case, any vertical line, so traveling parallel to the plate, that's going to be an equipotential line. So any vertical, in this case, any vertical line, any line parallel to the plate is going to be an equipotential. So if you travel along one of those vertical lines, you maintain a constant voltage. In other words, moving a charge along one of those equipotential lines involves doing no work because you're not changing the potential energy at all. And presumably, since the electric field points from a high voltage location towards a low voltage location, the region close to the plate is going to be high voltage. And the region farther from the plate is going to be low voltage. And if we had some numbers, we might even be able to label these. Maybe those are like, let's say, 50 volts, 40 volts, 30 volts, 20 volts, 10 volts, and so on. And then we could do the same thing in the other direction as well, also going from high voltage on the close to the plate region towards lower voltage in the far from the plate region. Any questions on that so far?
Can you repeat what you say about the potential energy something?
Yeah, that if you take if you look at the relationship between voltage and potential energy, in general, potential energy is test charge times voltage, because ultimately we're defining voltage as the ratio of potential energy over test charge. in the same way that we were defining electric field in the first place as the ratio of force over test charge. The idea being that two different charges will experience different forces because they have different charges, but the ratio of force over charge is consistent for a given location. And that ratio is called the electric field. Likewise, if you have two different charges, they're going to experience different amounts of potential energy. But if you take the ratio of potential energy versus test charge, you get a consistent ratio. And that ratio is called the voltage at that location. So voltage is defined as the ratio of potential energy of an object versus its charge, which means potential energy, if you solve for potential energy here, electrical potential energy is equal to charge times voltage. Or what we most usually care about is the change. So we could say change in potential energy equals charge times change in voltage, if you're moving a charged object from one location to another. If there's a difference in voltage from start to finish, that means there will be a change in potential energy, which presumably means it will take work to make that happen. And that amount of work, the change in potential energy, is the difference in voltage from location to location multiplied by the charge of the test object. Any questions on that so far? So for example, let's say we know the voltages. Let's say we know that this voltage is 100 volts. And let's say each one of these equipotential lines represents an extra 10 volts. So 100, 90, 80, 70, 60. So let's say this is 60 volts. If we take a charged object and move it, let's say we take a charged object and let's say we know the charge. Let's say this charged object is maybe positive 3 coulombs. So if we got a positive 3 coulomb object, and then let's say we move it. If we move it to a new location, let's say down here. So that's the new location of the object. That's going to involve a change in energy. And how could we calculate how much the energy changes?
So we need to find the delta V that is changing, moving from position 1 to position 2.
Yeah. And what do we know about the starting voltage and the ending voltage?
That the delta V at the ending voltage is smaller than the delta V from the starting voltage.
Well, the delta V is the path itself, not the final value, or we could say the final voltage and the initial voltage. So final voltage is lower than the initial voltage. And lower by how much?
By 40.
Yeah, so we'd say for this path, the delta voltage is negative 40 volts. In the sense that the voltage has decreased by 40 from start to finish, final minus initial. Note that that's not just the initial value or just the final value. The initial value is voltage equals 100 volts. The final voltage is 60 volts. So delta voltage, final minus initial, is negative 40 volts. So we could fill that in. And then what's the charge here?
Plus 3C.
Yeah, so we could fill that in as well, positive 3 coulombs. So positive 3 coulombs times negative 40 volts equals what?
120.
Yeah, and we got to keep the negative sign. Positive times negative will be a negative result. So negative 120. And what do you get if you multiply volts times coulombs? Yeah, that should be joules. In fact, if you take a look at the units here in the original definition, potential energy is measured in joules, charge is measured in coulombs. So voltage is joules per coulomb. And we abbreviate that as volts. Volts as a unit is joules per coulomb. So volts is joules per coulomb multiplied by coulombs. Coulombs cancel out and you get joules. So delta potential energy would be negative 120 joules. In other words, this motion, this moving along this path, involves a decrease in potential energy. And if it's losing potential energy, what else might you expect to happen? Where could that energy go?
Goes to kinetics energy.
Yeah, so one possibility of what might be happening here is it's losing potential energy, it's gaining kinetic energy, so it's going to be getting faster as it moves away from the positive plate. And again, that's something we should expect more conceptually. If you've got a positive charge and a positive plate, they're going to repel each other. So as the positive charge moves away, it gets faster and faster. From high voltage to low voltage, the positive charge is losing potential energy and maybe gaining kinetic energy. Or alternatively, maybe we're sort of holding it and guiding it. If we're holding it back and preventing it from getting faster, we'd be doing work. We'd be removing energy from the system, so a negative amount of work. Maybe we just let it move, in which case it's getting faster and faster as potential energy turns into kinetic energy. Or maybe we hold it back and let it gradually move at a constant rate, in which case we're doing negative amount of work by holding it back, preventing it from getting faster. But either way, it's losing potential energy as it moves from start to finish. Any questions on that so far?
Casey, let's say if we put the charge in between the equipotential line in between 100 volts and 90 volts, is that possible, or is it always gonna be on a specific equipotential line so we know the voltage?
Well, keep in mind the equipotential lines aren't physical objects. These are just markings we place on the diagram as convenient reference points. So 100 volts and 90 volts, it's not like the region in between doesn't exist. It's a gradual continuum from 100 to 99 to 97 to 98 to 97, 96, and so on. So the charged object could be anywhere. These aren't like the only allowed energy levels like in quantum mechanics. These are just markings on a map to show where some of the voltages are, but we can always fill in the in-between values. And if the object is in a location that's not specifically on one of the marked equipotentials, just use your best judgment as to how far in between it is. Like if it's exactly halfway between 100 volts and 90 volts, I'd assume that's about 95 volts. If it's much closer to the 100 volts, maybe it's 98 or 99 volts.
Thank you.
Any other questions on that so far? So it looks like the object started off with high potential energy and ends with low potential energy. On the other hand, though, what if we used a negative charged object? Let's say instead of being positive 3 coulombs, let's say this was negative 3 coulombs. What difference would that make? If we use a negative, if we use a negative 3 here, what would that do to the result?
You have a positive change in potential energy.
Right. If the charge is negative, then moving from high voltage to low voltage makes delta potential energy positive 120 volts. In other words, as it moves from high voltage to low voltage, it's gaining potential energy. So we would actually swap these. This negatively charged object starts at low potential energy when it's at a high voltage zone and is moving towards high potential energy when it gets to a low voltage zone. So for a negative charge, higher voltage means lower potential energy and lower voltage means higher potential energy because the negative multiplier reverses that. Note that we're still talking about a decrease in voltage. We're going from the higher voltage region to the lower voltage region. But since it's a negative charge, that means we're gaining potential energy as we do so. And where might that extra potential energy come from? How would you allow the potential energy to increase here? what might be happening as the potential, or to allow the potential energy to increase?
Increasing of kinetics energy.
Yeah, maybe it's losing kinetic energy. Maybe it started off at a high speed. Maybe we start here and throw it. And then as it moves away, it's getting slower and slower and slower, losing kinetic energy as it gains potential energy. Or alternatively, maybe you are doing work to it. Maybe you're holding this and moving it with a constant push. You're doing work to it to cause the potential energy to increase, perhaps. So this would be you could think of this as how much work it costs, how much work you have to do to it to make it move along this path without slowing down. So I think that's a very useful way of thinking about voltage. It's talking about much in the same way that we think of electric field as a location's capability to apply a force to a charged object. You could think of delta voltage as the capability of doing work to a charged object as it moves. So I think that's probably a very useful way of thinking about both electric field and voltage. Electric field is the capability of the location to apply a force to a charged object. Delta voltage is the capability of a path to do work to a charged object. Any questions on that so far? And one other thing I want to mention about charged plates. Let's say we put in another charged plate here. Any other questions on the equipotentials before I clear that part? Okay, let's take a look at it, bringing in another charged plate and see what happens. Let's say we put in another charge plate, let's say right here, and we have the same density of charge, but let's make it negatively charged instead of positively charged. So the same very, very large kind of plate with the same density of charge, because charge density is really what's important for these plates in terms of how much electric field they create. Ignoring the electric field I've already drawn here, let me blank that out a little bit. So ignoring that for the moment. The negatively charged plate is going to create its own contribution to the electric field. And what direction would we expect that contribution to be if we're looking at just the electric field created by the negatively charged plate?
Towards the negative charge plate.
Yeah, negatively charged source is going to create electric field pointing towards itself. So we should expect electric field pointing in the inwards direction, no matter how far, and the same strength no matter how far you are from it. So even if we get further away, we should expect the negative plate to be creating this electric field pointing towards that negative plate. So on the left side, that's going to be pointing to the right. On the right side, that's going to be pointing to the left. So that's the electric field. These darker orange arrows would be the electric field created by the negatively charged plate. But of course, we also have the electric field created by the positively charged plate. So let's combine those. If we want to find the actual electric field in these regions of space, how would we combine the vectors from the contribution vectors from both plates?
Adding vector.
Right, we'd add the vectors together. In this region on the left, if we add vectors to the left plus vectors to the right, what's going to happen?
Cancel out.
Right, those cancel out completely. So in this region, we have zero electric field. Likewise, on the right, we've got vectors to the right plus vectors to the left, same strength, because these plates, which are identical except for the type of charge, are creating equal strength electric field, just in opposite directions. So those cancel out. What about the electric field in between the plates?
Move towards the negative plates. So
Right, because we've got a vector to the right plus another vector to the right. Those combine to make a very strong vector to the right. So in the in-between region, we actually get this very strong vector pointing from left to right. So the overall electric field in this region is a very strong electric field pointing from left to right, from the positive plate towards the negative plate. And this very strong electric field in just the in-between region, it creates no electric field in the outside region. This is very useful for a lot of experiment setups. If you want to create a region with a certain amount of electric field for an experiment, typically what you would do is set up two parallel plates fairly close to each other and fairly large, charge up one of them with positive charge the other one with negative charge. And that's going to guarantee that you have a very strong electric field in a predictable direction in the interior region, and also uniform. It's the same amount everywhere. And no electric field in the outer region. So it's not going to interfere with other experimental setups you've got nearby. So it's a very useful way to establish a controlled and contained electric field in this small region of space. Also, how would you control how strong the electric field is here? How would you set up this experiment if you want to create an electric field with a certain predetermined strength?
do we add more charge in it?
Yeah, the amount of electric field, the strength is going to be determined by how much charge is on each plate. So if the electric field you've got isn't strong enough, you can just cause the plates to accumulate more charge, attach more charge to each plate, and you get a stronger electric field. Or partially discharge the plates and you get a weaker electric field. Also, if you take a look at the equipotential lines, what would the equipotential lines look like here?
Perpendicular and straight down with the electric field.
Exactly. Once again, we've got these perpendicular, in other words, vertical. And since the electric field is very strong, these are going to be very close together. These should be equidistant. I'm not quite managing that, but as the general idea. So these are going to be, these represent the equal amounts of change in voltage. Like maybe each jump from line to line represents another 20 volts or something like that. And which region would you expect to be the higher voltage versus the lower voltage?
Low voltage will be on the negative plates.
Yeah, the positive plate is associated with high voltage, the negative plate is associated with low voltage because electric field points towards lower voltage regions. So we get a low voltage region on the right side and a high voltage region on the left side. And in the outer regions, if the electric field is 0, what does that tell you about voltage?
Zero.
Well, the voltage isn't 0, but yeah, it's not changing. The change in voltage would be 0. Because electric field always points in the direction of decreasing voltage. If there's no electric field, that means there's no direction that would cause voltage to decrease or increase. In a region with no electric field, the voltage is just some constant value. So this entire region has constant low voltage. And this entire region on the left side of the plate has constant high voltage. But in the in-between region, we get this rapid transition of voltage from location to location. So that's the big deal that's going on in here. We get this transition from high voltage to low voltage. Which means we can say this entire positively charged plate is at a very high voltage. This large negatively charged plate is at a very low voltage. And where have you seen a mechanism like this in a previous quarter?
A capacitor?
Exactly. This is a capacitor. You've got two parallel plates with a gap in between. Put positive charge on one of them, put negative charge on the other, and you get a voltage difference that is proportional to how much charge is on the plate. Specifically, delta V of the capacitor is equal to charge over capacitance. The more charge is accumulated, the more the difference in voltage is. So this is exactly the same as the capacitors we were looking at in 7b with circuit diagrams. It's just that we're now looking at what's actually going on inside the capacitor. It might help if you imagine like a wire attached to each one of these plates. So these wires go off somewhere else, and this difference in charge creates an electric field inside the capacitor only, which creates a difference in voltage. That difference in voltage can now be used, for instance, to drive current around the circuit. Maybe this is connected to a light bulb or something. So this is ultimately why a capacitor works. The difference in charge creates an internal electric field, which implements a difference in voltage from one plate to the other. And that's exactly the delta V capacitor we were talking about in 7b. Any questions on that capacitor or those parallel plates in general? All right, then let's take a look at this idea of dipoles, something else that's also influenced by electric fields. I'm going to clear the capacitor drawing for now. Let's say we have a electric field. Let's say the electric field is, say, straight up. And let's say it's a uniform straight up electric field, same strength everywhere and same direction everywhere. So let's say this is the electric field. What would be an easy way to create an electric field that's straight up everywhere?
Are you asking where to put the plates?
Yeah, we could have horizontal plates. Maybe, for instance, we could have one horizontal plate below with what kind of charge?
Positive charge?
Yeah. Positively charged plate below. Or alternatively, we could have a negatively charged plate above. Either one of those would create upwards electric field. If we implement both, using that parallel plate setup from earlier, we get a very strong uniform electric field that's easy to control in the interior region and no electric field in the exterior region, or at least a very weak electric field on the outside. So anytime you've got a uniform electric field in some region of space, it's reasonable to assume that that at least could have been created by a parallel plate setup like this. You don't actually need to know the source charges. The whole point of the electric field is that you can just treat the electric field as creating forces and ignore the source charges. But it's often useful to imagine that this electric field was created by a positive plate on one end and a negative plate on the other end. So keep that in mind as we go forward. But also remember, you don't actually need to know what the source charges are. We just need to know the electric field in this region of space. And let's say we put not just one charge, because we've already dealt with what happens if you put a charge in this region. But let's say we have an object with a pair of charges. Let's say you've got like a plastic rod with a positive charge on one end and a negative charge on the other end. Let's say you've got charge positive Q and then another charge with the same amount of negative charge somewhere else. Let's say over here, negative Q. And let's say these are linked together by a plastic rod. So simplest example, let's say we've got maybe two ping pong balls, one of them that has been charged positive, one that's been charged negative, and they're linked together by a plastic rod that they're glued to. So this is one object. It's just got a positive charge on one end and a negative charge on the other end. We would call this a dipole, and specifically an electric dipole. And an electric dipole is essentially just any object where you can draw a line that splits it into definitely a positive end and definitely a negative end. Like if we just draw this line, I guess it should really be a line through the center of mass. We can draw a line that splits this up into an end that's more positive and an end that's more negative, or a more positive half and a more negative half. So we call this an electric dipole. Dipole meaning two polarized ends. One end that's polarized as positively charged, the other end that's polarized as negatively charged. And if we take a look at this as just one big object, what's the total charge of this object?
Neutral.
Yeah, it's neutral, zero charge in total. So how much force should we expect it to get from the uniform electric field?
Zero.
Yeah, it should experience zero force from the electric field. And we can even see that by looking at the individual charges. Like this positive charge alone should get a force in which direction?
Away from the positive plates, but the same direction with the electric field.
Yeah, I would recommend ignoring the sources and looking at it in terms of what's the electric field doing. The electric field creates force in that same direction on a positive charge, which is also away from the hypothetical positive plate and towards the hypothetical negative plate. But the whole idea of the electric field is being able to determine that without even knowing what the source charges are. So on the positive plate, or positive charged object, we get a force in the same direction as the electric field. And what about on the negatively charged object? Yeah, it's going to be downwards because that's in the direction opposite to the electric field. Again, going back to the idea that force equals charge times electric field. In this case, the charge is a negative value. If you multiply a vector by a negative scalar, you get a vector in the opposite direction. So for the negatively charged object, the force is in a direction opposite to the electric field. And from this, we can see that these two forces are opposite directions, but the same strength, because they're both the same amount of charge times the same strength electric field. So these vectors add up to zero, and this neutrally charged object, this dipole, experiences no net force. So there's going to be no translational acceleration. But the forces add up to zero, but what doesn't add up to zero here? What else do these forces create that we saw in 7b?
Is it torque?
Yeah, these forces create torque because these are off-center forces. So if we look at this in terms of torque, as we saw in 7b, torque is always defined relative to some pivot point. If you just got this object that's free floating in space and it's able to spin, what location on the object would you expect it to be spinning around? What should we use as that center of rotation?
The center of the handle connecting the two objects, the two charge.
Exactly, that center point, typically the center of mass. Like if this is some object with mass, we would use the center of mass as the pivot point. Since it's not really attached to anything, it's just able to spin freely in space. So we should treat the center of mass as the pivot point, which means we would be measuring everything from there. And going back to the torque stuff from 7b, torque, how do we usually calculate torque? Or how do we find the direction of torque? Because that's really what's going to matter here.
The right-hand rule?
Yeah, we can use the right-hand rule. And yeah, the amount of torque, the magnitude of torque is going to be radius times force times sine of the angle between them. So if we draw out the radius vector is just going to be a vector from the pivot point towards the location where the force is located. So this radius vector that radius and this force, and then of course we'll multiply by sine of the angle between them. But that angle is not 180 degrees or 0 degrees, so it is going to be some non-zero number. So we do get some torque here. And for the direction of the torque, we can use the right-hand rule. Before you even use the right-hand rule, we've got this radius and this force. The torque has to be perpendicular to both of those. What are the only two possibilities that are perpendicular to the radius and perpendicular to the force here? If we've got radius this way and force this way, those two vectors form a plane. What directions will be perpendicular to that plane?
What direction, you asked?
Yeah. Because in general, the torque is perpendicular to the radius, and the torque is always going to be perpendicular to the force. What directions, or what are the only two possible directions that are perpendicular to the radius vector, this one, and perpendicular to the force vector? Left and right would be perpendicular to the force, but they wouldn't be perpendicular to the radius vector. You got to think three-dimensionally for this one. What are the only possible directions that are perpendicular to this direction and perpendicular to this direction?
Is it out of the board and into the board?
Yeah, outwards and inwards. Because these two vectors span the entire plane. They're occupying both dimensions, up, down, left, right, in the plane of the screen or the board or whatever. The only way to get perpendicular to both of those is to leave the board and go outwards or inwards. So the only possibilities for torque in this scenario are straight out and straight in. It won't always be out and in. It's going to be whatever two directions are perpendicular to both the radius vector and the force vector. But in this case, outwards and inwards are the only possibilities. So the right-hand rule is basically just to choose one of those two. Once you've narrowed it down to two possible directions, the right-hand rule will choose one of those two directions. In this case, we got radius and force. So if you take your right hand, stretch your right hand in the direction of the radius vector, so up and to the left, and curl your fingers in the direction of the force, upwards. And your thumb should be pointing inwards, I think. Again, that's put your hand at the pivot point, stretch your fingers straight in the direction of the radius vector, and swivel until you can curl your fingers in the direction of the force. Your thumb should tell you the direction of the radius vector. So I think that's going to be inwards in this case. Inwards, so we would draw that as an arrow pointing into the page, usually drawn as a circle with an X. So that's a torque in the inwards direction, away from the viewer. And what about for the negative charge? If we draw in this radius vector and this force vector, we're again going to get either inwards or outwards in this case. Use the right-hand rule. Is this torque going to be inwards or outwards?
Inwards.
Can you stretch your, what was that?
Inwards.
Yeah, it's going to be also inwards. You stretch your fingers in the direction along the radius vector, swivel until you can curl downwards, because that's the direction of the force, and your thumb should be pointing inwards. So that means this is also an inwards torque. So what happens if we add these torques together?
They cancel each other out?
If you've got an inwards torque plus another inwards torque, those are two vectors in the same direction. So what happens when you add them?
Oh, so they add up?
Yeah, they're going to combine. Yeah, twice the amount, assuming these are equal charges, equal amounts of charge. So as forces, the forces cancel out because they're in opposite directions. But the torques are in the same direction as each other. So that means these torques are going to combine, and we're going to get a very strong torque. And ultimately, that torque is going to create a tendency to rotate the object. The object is going to rotationally accelerate in the I guess that'll be the clockwise direction. Because the whole point of the direction of torque is it tells you which direction this is going to rotationally accelerate. So point your thumb in that direction, and the curl of your fingers tells you the direction this is going to rotationally accelerate. So that'll be something like in this direction. So this object is going to start spinning in the clockwise direction as a result of this torque. So ultimately, that's what happens to a dipole in the presence of an electric field. If we're treating the dipole as a test object in the presence of an electric field from some other source, a uniform electric field creates no net force on the dipole. The forces cancel out. But it does create a net torque, which is going to cause the dipole to start to rotate or to rotationally accelerate more generally. And it's going to keep rotating. Is there any circumstance in which the rotated dipole would experience no torque at all? What would be the equilibrium alignment where there's no torque? If it's horizontal, let's try that. If we've got a horizontal, say positive, negative, and they're joined together. In this case, if we take a look at the forces, the positive charge is still getting a force upwards, the negative charge is still getting a force downwards. So the forces cancel out. But what can we say about the torques? If we've got, again, measured from the pivot point, this radius vector there, and this radius vector. In this case, what's the angle between radius and force? Yeah, they're perpendicular. And what's the sine of a right angle? So we end up with torque equals radius times force times 1. That's actually the largest it can be. So if the dipole is oriented perpendicular to the electric field, we get a very strong torque, which means it's going to rotationally accelerate quite a bit. But what orientation is going to lead to no torque at all? How would we arrange this if we wanted no torque?
Vertically?
Yeah, if we arrange this vertically, specifically if we put the positive charge above and the negative charge below. So something like this. In that case, if we fill in the forces and the radii, so radius, radius, and force and force. At this point, what's the angle between radius and force?
80.
What was that?
Oh, sorry, 0.
Yeah, since they're in the same direction, I would call the angle between them 0 degrees. And what's sine of 0 degrees?
0.
Right, which means this experiences no torque at all. It's not so much that the torques cancel out, it's just that each one experiences no torque because of the angles. So this is a stable alignment. If you got the dipole oriented parallel to the electric field, you get no torque at all. So this is a stable equilibrium. In fact, note that when it's out of equilibrium, the torque is pushing it towards aligning with the electric field. So you get a torque pushing it towards equilibrium. If it's at equilibrium, you've got no torque at all. So if it's there, it'll stay there. Although if it's in the process of rotating and hits equilibrium, it'll keep going because of the momentum and then get pushed back towards equilibrium. So it'll sort of wobble around with equilibrium as what it's eventually settling down on. If there's no friction, it'll just keep wobbling back and forth forever. But if there is any friction, it'll eventually get smaller and smaller oscillations and settling down on equilibrium as the final equilibrium it approaches. So eventually this dipole, if there's any friction, will settle down to align with the electric field. And you can use this as effectively an electrical compass. If you take like a small sliver of plastic, charge one end positive, charge the other end negative, and mount it on a hinge and allow it to swivel. If there's an electric field, it will swivel to align with the electric field. So you can use this to detect the presence of an electric field and what direction it's in. In fact, a very useful tool here would be to have many of those little plastic slivers in sort of a grid. Then if there's an electric field, those will all snap to show the direction of the electric field at each location. Any other questions on the electric dipoles so far? All right, then I think that's it for today. Let me know if you have any other questions, and I will see you next time.